Good morning. Can everybody hear me okay? Perfect. Yeah, great. For once my talk isn't before lunch, so that's great, and everybody's still hyped on caffeine. So let's start a bit about me. My name's Isaac. I live in Estonia. I'm currently a research engineer at Clarify, and I help build and maintain our multimodal retrieval system on the AI platform. These days I'm working on improving our vector search capabilities and enabling new generative AI tech in production. And my background was in aerospace engineering, and it took quite a few hops to land into AI. But today we're going to talk about RAG. Raise your hand if you know what RAG is. That's at most of the room. Great. Raise your hand if you have tried some kind of RAG prototype. Okay. Raise your hand if you have a RAG pipeline in production. Okay, way fewer hands. Okay. Great. So with that in mind, let's begin. So our talk today, its title, has two meanings. One refers to how LLMs have intrinsic knowledge barriers, like how they have like an up to certain date, and how RAG provides the LLM a gateway to overcome that barrier. And the second one refers to the knowledge barrier we face as developers in today's AI landscape that is ever-changing. It's kind of crazy how much progress there's been already between when I submitted the talk and when I'm giving the talk. So today I'd like to start with a vanilla RAG pipeline and dig a little deeper into each component's customizations and parameters to help us understand why they're needed and help you make a better informed decision on choosing the best tools for it. So let's start with what RAG is, but if most of the room know that already, I can go a bit quicker on this part. So LLMs have proven to be quite capable when it comes to general topics, because chances are they have received a lot of training data for them. In this example, I asked ChatGPT what an astronomical unit is, and it gave a correct answer. But when asked about topics they haven't been trained on before, LLMs are quite limited. The two main limitations of LLMs are that they are, one, static, and two, they lack domain-specific knowledge. For one, LLMs have a static knowledge base that ends at a certain point in time. Some of you may know this already. ChatGPT, for this example, its cutoff is January 2022, which explains its response when I asked about the speakers at this conference. For number two, when LLMs encounter gaps in their data, they might say they don't know, or worse, generate plausible but inaccurate information. These aren't necessarily solvable by prompt engineering when the knowledge is missing. So we can use RAG, which is a method that addresses these two main limitations by combining LLM and information retrieval. So there's no shortage of information these days on RAG architecture. We can start with the simplest vanilla setup, which consists of two main stages and 5 main components. From the left, it goes read, chunk, embed, retrieve, and generate. The first 3 are in the index stage, while retrieve and generate are in the query stage. We start with some data or specific knowledge, and they can be found in many places like Notion pages, Google Docs, Slack, Confluence, S3, you get the idea. Those data are read from the source, split into smaller chunks, then transformed into vector representations called embeddings. And those are then indexed by the vector DB. Whenever a user sends a question, that question goes through the same embed stage. And then that query embedding is used to compare against the embedding stored in the vector DB. At this point, the vector DB finds the most similar embeddings to the query embedding, and then returns the most similar chunks. These chunks are then fed into a prompt as context, which is then fed into an LLM to generate an answer. Okay, now that we understand how RAG works, which I think most of you do, and what it's for, let's take a look at how to build it. Of course, we can write everything from scratch, but maybe we could avoid reinventing the wheel here. There are a lot of options for a framework and tools built to build RAG with, especially open source ones. Some of the popular ones are Llama Index or LangChain. You might have also heard of Verba from Rereate or Haystack from DeepSet. I think OpenAI has their own offering as well, but you and I both know why some people prefer alternatives. Regardless of which framework you choose, you will need to choose a provider or a library for each component. A classic consideration when it comes to how to choose a tool is self-hosted or cloud or managed. Almost every component has a managed offering these days, and it really depends on how much time and resources you have or you're willing to spend on maintaining your own stuff. Others say keep it mainstream, but maybe relying on GitHub stars or word of mouth, like on Reddit. But some blog posts also suggest that avoiding bad is more important than finding the best. So does this tool integrate well with your current stack and pipelines? Is it simple and easy to change if you regret your decision? Is it easy to debug? Is it over abstracted? With that in mind, let's try to understand each component of the system so you can make that decision yourself. Each rack component is very specific and focused, and I think it might as well be, you guessed it, a startup. Notably, these are some of the companies that have recently raised a funding round. As expected in very specific and highly focused companies, each company's offering also tends to come with a lot of options and customization possibilities. So there are also tutorials, cookbooks, full-on Colab notebooks for us to walk through step by step. But before we follow the RAG and X lines of code starter tutorials, it's probably best to first understand why those are the defaults and what else we can choose from and why those options exist. Let's start with the first component, which is read. This part is really about loading and reading your data into a format that is easily parsed and chunked later on. Nothing really fancy here. One main consideration, I think, for this component is more related to how often your data is changing. If your source is static, for example, like the Dune book series, which is better than the movies, then this whole stage is likely not going to be revisited much. If your source changes often, like quarterly financial reports or your internal docs, like my internal docs from my company, then you might want to consider a more automated option for this ingestion. Next up is chunking. We need chunking because pretty much all models have context limits. This applies to LLMs, and this applies to embedding models, and we'll revisit this later. Chunking also helps optimize the relevance of the retrieved content, so how we split up a document is very important. Usually, your parsed text does not look this neat. In some tools, the default chunking strategy is to use common separators like the new line character to give fixed chunks with some overlap. But as we know, applying a generic method to a specific problem doesn't always work. So it's important to consider what type of data or documents you're using. If the default is some sort of character level chunking, a natural next step would be to consider some content-aware chunking, for example, at the sentence level. Some more document-specific would be chunking methods for Markdown, LaTeX, or HTML, where the original structure and format of the content is taken into consideration when creating the chunks. Chunk size is also a key factor. As it turns out, if the chunks are too big, for example, if you take the whole section or the whole chapter, we add too much noise in the embedding. And if the chunks are too small, like one sentence, we tend to lose too much context around what the sentence is about. So the goal is to find a balance where the chunks are able to capture some specific meaning from the sentences and also retain enough contextual information around other sentences and phrases. The next one is embedding. In my opinion, this is the most underrated component of the whole RAG pipeline because LLMs and vector DBs these days get a lot of the spotlight and hype. This component may not have many parameters to tune in the API call. So some of the main questions we ask here are, one, which model should we choose? And two, how often do we want to call it? You might be familiar with names like Cohere, OpenAI, or Gina when it comes to embedding providers, but there's more. There are a lot of models to choose from. The main factor to consider would be whether you want to figure out hosting yourself or use a cloud API and just call it a day. After that, you can compare models within that bracket. What I've seen people use is the Massive Text Embedding Benchmark, also known as MTEB. But being first on this benchmark doesn't mean that it's best for data. Some models at the top ranks can be quite large, and that usually correlates to inference speed. So you might want to consider lighter models if you prefer to build and iterate faster. Embedding dimensions could also be a factor because it directly affects how much storage is needed. Without any quantization, embeddings usually use float 32, so that's 4 bytes. At 1,024 dimensions, one embedding is 4 kilobytes. So 1 million of those takes up 4 gigabytes. You can extrapolate for the other dimensions and if you have more embeddings. So if that's an issue, maybe it's worth considering using lower dimensions, some kind of quantization for your embeddings, or more recent advances like the Matryoshka embeddings. That's like the Russian nested doll. I don't know if I'm saying it properly. Also, I mentioned earlier, like LLMs, embedding models also have token limits. So this may affect the chunk size as well. If the chunk exceeds that limit, the remainder is not embedded, which I don't tell you that. So that might be some information lost there. Now we move on to the query stage with retrieve. A common question that comes up with retrieval is which vector DB to choose, purpose-built or traditional DBs with vector capabilities. There are many blogs on this very question. Mostly evolve around speed, recall, and cost. In terms of speed, it depends on the latency requirements of your application. Speed also depends on how much data you expect to handle. Below a certain threshold, like 10 to 100K, the difference really isn't that noticeable. Oftentimes, speed and recall is a trade-off, so it's important to understand which one is of higher priority, and that usually helps you decide which index to choose from. For cost, we always come back to the question whether you have the time and resources to manage the services, scaling, backups, upgrades by yourself. If you or your team already have the capabilities to support on-prem hosting, then managed solutions on the cloud may not make the most sense. So regardless of which provider you choose, you can still tune a few parameters. One of these is K, as in top K most similar results. These retrieve chunks will be used as the context for your LLM prompt. So given that chunk size is fixed, if we set K too high, then the context gets very long, and the LLM can suffer from something called the lost in the middle problem. This is when the LLM tends to generate incorrect responses if it generates incorrect responses if the needed information is somewhere in the middle instead of the beginning or the end. This problem is easily noticeable in models that had shorter context windows, like 4K to 16K, which is what was used in the original paper. So you can imagine how noticeable the problem would be when using models with even bigger context windows, like GPT-4 Turbo, which has 128K, which is like 1,000 tweets. So one way to mitigate this problem is to use a smaller K to reduce the given context. But this may not work on all use cases, especially when the question needs longer contexts to be answered. So another way of addressing the lost in the middle problem is by using a re-ranker. A re-ranker is a language model that directly compares the query with the documents and gives a similarity score for each pairing. The results are then sorted by these scores so that the most relevant chunks are on top. We can first retrieve a higher number of chunks from the vector DB and then return the top K output from the re-ranker to the LLM. This kind of two-stage retrieval problem is not new. It has been around for a while in the information retrieval community. But re-rankers are slower. So before we jump in and add it to our RAG pipelines, we must consider whether it suits our needs. and if other chunking or retrieval techniques have already been exhausted. Separately, there might be scenarios where you want to keep the vector search capabilities, but also require exact phrase matching for specific terms like product names. This is where hybrid search can be helpful. And usually you can tune how much you rely on more, the vector search or the keyword search. Okay, finally we have the generate component. Some of you may already be well versed in this. This component is about options around using an LLM. Whether you choose to host a model or use a cloud API, there are a few things to consider still that may help you either reduce your headache or your bill. One of the top reasons for bloated bill or unexpectedly high latency when calling an LLM is not having an output limit. We can leverage the prompt to the LLM to achieve that. For example, saying that to use 3 sentences maximum and keep the answer concise. You can also consider imposing a harder limit by using the parameter max tokens or a variation of this parameter. Another parameter that may cause headaches is temperature. It's often set between 0 and 1. Increasing temperature would lead to more randomness, which encourages more diverse and creative outputs. For tasks that require more creativity and varied responses, you can use a higher temperature. But in RAG applications where the task is more fact-oriented, a lower temperature is usually better. So sometimes this is default at 0. If after fiddling with all these options in vanilla RAG, you're still unsatisfied with the results, we could take a look at more advanced techniques. Some involve agents, hierarchical chunking, or recursive retrieval, just to name a few. I won't cover these here. Instead, I'd like to mention 2 things that are important, but not often mentioned in quick start guides. The first item is chat memory. We have talked about how RAG injects relevant information into the context for chat generation. Being able to retain that context for multiple turns is very important for a smooth chat experience. As you may know, LLMs are stateless, which means they won't remember what you have sent it before. So by default, you need to maintain the state on your side before passing to the LLM. What this means is before asking a follow-up question, you also need to pass in all the previous messages from both sides of the conversation. Some tools offer add-ons for chat memory or chat history. Otherwise, you can manually append them to your growing list for every chat session. But that's not the end. LLMs have fixed context windows. So eventually, we keep appending past messages into the next prompt. We'll use up that context window. Plus, the longer the context, the more time it takes the LLM to read the context. So that adds to the latency of the pipeline as well. So what we could do here is to shorten the current context by trimming it, or only keeping the last n terms, or using summarization and generate one shorter message. There are more advanced techniques that deal with long-term memory, like adding a call to the LLM to rephrase the question based on chat history. The second item is evaluation. Just like any other system, it's important to understand how well it's performing and how much improvement has been achieved over the baseline. This doesn't just involve measuring how fast or how much it costs, but also how good the outputs are. For how fast, in addition to monitoring the round-trip time, we could also enable tracing to understand latency of each component. Some tools offer it for free, some paid, or you can instrument it yourself with something like OpenLLMetry. For cost, that could be an aggregation of all your cloud API bills or infra bills, engineering time, depending on your setup. As for how good the outputs are, the simplest method of all would just be to print the inputs and outputs of each stage. Once you have those, you can apply some RAG-specific evaluation metrics separately on the retrieval and generation stages. For example, for retrieval, the goal is to find, given a configuration like your chunking strategy and your embedding model and your retrieval strategy, how well can the system retrieve relevant results? Here you may need a golden set of query and ground truth pairs of relevant documents. You could also use information retrieval metrics like NDCG, but for RAG, it's more meaningful to understand your signal-to-noise ratio of the retrieve context and how well it can retrieve all of the relevant information required to answer the question. For generation, the goal is to find out, given the relevant documents, how factually accurate is the generated answer and how relevant is the generated answer to the question. There might also be some custom metrics that you're interested in, like whether a certain document is cited or whether the response is too long. There are also RAG eval tools like Ragas and Phoenix to help automate this process. So it's safe to say that RAG has quite a few components, and there are also a lot of places where it could go wrong. When choosing between tools and managed solutions or writing your own, it's important to understand the needs of your application. Newer isn't always better. And that's it from me. Here's how you can find me later if you have feedback on the talk or questions. And thank you very much.
Questions?
Yeah.
Great.
Thank you for the presentation, Isaac. I just wanted to ask you, do you think that rack systems will eventually fade out as the AI scales up and they're like smart solutions to generate context with responses with the context you want? Is it like a 1-year gap, 2-year gap, or is it just going to be a staple?
The question is whether I think the rack system will fade out.
Yeah.
We're looking for like a rack killer. I think that term has been being floated around for a while. I don't think anytime soon. I feel like it would change a lot on how we do this retrieval, probably in a smarter way or more efficient way. Like vanilla setups usually just retrieve every single time. But I think there are already a few papers that come out that talks about generating tokens to tell you whether to retrieve this response or not. And treating RAG as more like a tool usage. So I think we're trying to figure out how to do this smartly, but whether this will be eradicated or not is very hard to tell. Thanks.
Okay.
I have a question. Thank you for the talk. It was very interesting. The question is, the recall metric for retrieval scales not that good, depending on the number of tokens. Would you still recommend it, even though, like, at certain scale you can tell with certainty if your recall number is actually accurate or not?
Can you repeat the second part of the question?
Right. So basically, if you have like 100,000 of documents, you wouldn't be able to say like, okay, is this recall actually accurate or not? Because it would be then you would have to like evaluate through all the 100,000 documents. So the question is, would you say it's still useful even though it's not accurate on scale?
Yeah, I guess if you have a large if your recall metric is based on a large number of documents, meaning I'm assuming you mean you need all those documents to answer that one question.
Recall is basically
yeah.
How much is actually accurate?
How much of the entirety of
yes.
the ones that you want, right? It becomes hard when you have long context conversations like that. I wouldn't say one metric rules them all. I would say let's pair it with something else. A lot of the time, well, NDCG works with ranking of your retrieve results. I think top-end precision would be another good one as well if you limit to just looking into whatever you retrieve. But I feel like that would be a very interesting case if you really need a lot of context, which kind of begs the question whether that could be fine-tuned on if you need a lot of specific domain knowledge than using something like RAG. Yeah, but that's a very interesting case. Thank you.
Thank you. Sorry. Time is up. I'm sure you can see him outside.
I will ask in private.
Yeah, I'll be around.
Okay, great. Thank you.